Hello everyone, this is Tom from Marvell. I'm presenting our work adaptively compressing IoT data on the resource-constrained edge. I will first introduce the background of this work. Then I will present the design of our ZipMate adaptive compression design. I will also present the IoT datasets we collected and our preliminary evaluation of ZipMate on these datasets for edge-to-cloud data transfer. Finally, I conclude my presentation and discuss our future work. IoT ecosystem are generating big data. IDC predicts that by 2025, there will be 41 billion connected IoT devices, generating more than 79 zettabytes of data. According to a NSF data storage research report, IoT brings on an explosion of data collection, storage, and processing demands. It's crucial to identify and reduce IoT data in a timely fashion. In edge cloud system architecture, big data are collected at endpoints, analyzed on the edge nodes. Currently, there's an emerging trend that data are moved from edge nodes to cloud servers for deep analysis. The data movement crosses wide area network, which has low bandwidth. Edge cloud data management is facing big challenges. The challenges are twofold. First, the edge-to-cloud data transfer time is long, which delays domain scientists to gain insights from the deep data analysis because of the wide area network bottleneck. Second, the cloud storage costs of explosive IoT big data will be huge. We believe data compression can mitigate these challenges. Compression-based data transfer consists of 3 steps, and they can be pipelined. First, data need to be read from disk into memory. Second, data are compressed in memory. Finally, compressed data are transferred from edge to the cloud through wide area network. Storage bandwidth can easily achieve several hundreds of megabytes per second. Compression and network transfer throughput is usually tens of megabytes per second. Therefore, CPU-bound data compression and network-bound data transfer are the main bottlenecks. Because of the resource bottleneck, the compression-based data transfer faces a challenge. That's the compressor selection. In IoT environment, we have different types of files, like the image, video, and of the other types. On the other hand, we have different compressor choices, and the different compressors have different performance on different data. Therefore, for a specific data, the challenge is which compressor to use for it. To solve this issue, we propose ZipMate, which implements prediction model to adaptively select the best compressor for a specific dataset at the system runtime. When designing ZipMate, we have 2 application scenarios in mind. The first scenario is computation offloading. That's IoT data need to be moved from edge servers to cloud servers for deep analysis. In this case, we aim to accelerate the data transfer so that the analysis of IoT data in cloud can be launched as soon as possible. The second scenario is storage offloading. That IoT data need to be moved from edge to cloud to release storage space, or for data archiving. In this case, we aim to reduce data volume as much as possible so as to maximize cloud storage cost savings. For optimal compressor selection, we can simplify the data transfer throughput as the minimum of real-time CPU compression throughput and the product of available network bandwidth and compression ratio. In scenario 1, the optimal compressor is the one that can deliver maximum data transfer throughput in terms of uncompressed size. In scenario 2, the optimal compressor is simply the one that can achieve maximum compression ratio. Predicting the compression ratios of a dataset with different compressors is the key. Currently, we simply use small data samples to predict the compression ratio of 4 datasets. Basically, we use prefix sampling to get the first 1 MB of data from the dataset. We compress this sample to predict the compression ratio of the 4 datasets. And we know this naive method is not accurate, and we are enhancing it. Because there is no specific IoT dataset repository publicly available, we screen multiple IoT datasets out of the generic public datasets repository and study IoT compression on these datasets. Some data are collected from typical IoT devices, such as smart farming application sensors, which record soil moisture data. Some datasets are not claimed to be collected by IoT devices, but their application scenarios could be typical or emerging IoT scenarios. We conducted data compression on these datasets with 4 general-purpose compressors: gzip, bzip2, lzma, and zstd. We have implemented the ZipMate adaptive compression components of the system and published our source code on GitHub. We evaluate ZipMate on the different number of CPU cores and different network bandwidth configurations to emulate different resource constraints. All compressors are in their default speed mode. We made the following observation. First, network bandwidth and computing power both have obvious impact on end-to-end data transfer time, but the bandwidth dominates the impact. As the figure shows, in general, the edge-to-cloud data transfer time decreases when network bandwidth or the number of the CPU cores increase. For example, with 1 core for compression, when network bandwidth increases from 10 to 20, 40, and 80 megabits per second, the average data transfer time dramatically reduces from 145 seconds to 81, 57, and 50 seconds respectively. With 2 or 4 cores for compression, increasing network bandwidth has a similar impact on data transfer time. In comparison, the impact of increasing CPU cores for compression is not as much as increasing network bandwidth. Second, there is no single compressor which performs best in all or even most cases. Third, our resource-aware adaptive compressor selection scheme consistently outperforms unitary or random solutions. On average, our adaptive compression outperforms unitary compressor selection by 10 to 31%. In scenario 2, compression ratio is the most significant metric, and we made same and similar observations as scenario 1. Basically, we also observed that there's no single compressor which performs best in all or even most cases to achieve the best compression ratio. And similarly, the resource-aware adaptive compressor selection scheme consistently outperforms unitary or random solution in achieving the highest compression ratio. To conclude, our preliminary study shows that for a dataset, different compressors show different performance. In resource limitation conditions, data transfer is limited by various runtime resource bottlenecks, including available CPU resources and wide area network bandwidth. And the resource-aware adaptive compressor selection mechanism proposed by us can considerably accelerate edge-to-cloud data transfer or improve data compression ratio. This work is far from complete. We plan to extend our current work in the following directions. First, we plan to build and enhance compression ratio prediction models for different compressors, and we believe this is the key and core of our work. Also, we plan to run representative edge workloads to measure the performance degradation of this application caused by compression, because we know compression is resource consuming, and we may propose solutions to mitigate this impact. Third, we plan to investigate the security challenges in IoT, edge, and cloud environment to enforce proper data security policies in our middleware. Actually, when we designed the ZipMate API, we have reserved a parameter to allow users to specify encryption the data at the client side before the data is sent to the cloud. Thank you, and I take question.